All right, so we're picking up where we left off in the last video. We had talked about linear dependence and linear independence in the context of solutions to linear systems, solution vectors to be a little bit more accurate. And now we're going to talk about this next theorem, which is, again, mimicking something in section 4.1, criterion for linearly independent systems. So if you recall back in section 4.1, we talked about needing a linearly independent set of solutions to a homogeneous differential equation. And if it was an nth order linear homogeneous equation, we would need a total of n solutions that formed a linearly independent set, and then we can construct the general solution to that out of those n solutions, which we call the fundamental set of solutions. We're looking for basically the same thing here, and the way we're going to determine if a set of solutions is linearly independent is essentially the same way. We use the Wronskian. However, the Wronskian looks a little bit different here, simply because we're not taking the Wronskian of a set of functions anymore. It's a set of solution vectors, and each vector contains a set of functions in its own right. So here, what we're looking at is a set of column vectors, solution vectors to a system of homogeneous system of equations, and we're assuming there's solutions on some interval I. The Wronskian, in this case, we define it to be, again, a determinant, an n by n determinant, but this time the columns of this determinant are simply the columns, these column vectors themselves. So there's no derivatives being taken the way that we do in the case of section 4.1 when we're looking at the Wronskian. We're literally just taking the columns as they appear in the solution vectors and putting them together into a determinant. If this determinant is non-zero for every t in that interval that we're looking at, then the system is linearly independent. And so that way it's a similar result as what we saw in section 4.1. Also, just like in section 4.1, we get a little bit more. If the result of this is equal to zero for, the result of this will either be equal to 0 for all t on the interval or no t on the interval. So that kind of helps when we're checking that criterion. I talked a little bit about the fundamental set of solutions already, but it's the same idea with systems of equations as it was in section 4.1. So if you have a set of n linearly independent solution vectors of a homogeneous system, and again it's referencing 5, but what this is supposed to reference in the book is a system of n equations with n unknowns. Notice the same n is the number of solutions here. So if we can find a total of n linearly independent solutions to that homogeneous system on some interval I, then we call that a fundamental set of solutions, just like we did back in section 4.1. Okay? This next theorem guarantees that that a homogeneous linear system will always have a fundamental set of solutions. So we're not going to run into a case where we can't find that fundamental set of solutions. We'll always be able to find one. In addition to that, the way that we use the fundamental set of solutions to form a general solution to a homogeneous system is the same as we did back in 4.1 as well. If you've managed to find a fundamental set of solutions, then the general solution to our homogeneous system is simply the set of all linear combinations of these, which is what this denotes here. Okay, so what we are asked to do in this example is we're given a system, but we're not shown what the system looks like explicitly. We don't know what A is equal to. However, we are told that we have a total of three solutions to this system, and it's actually I left out an important piece of information here. We need to know that this is a 3 by 3 system. 3 equations, 3 unknowns, because that would mean that we have the correct number of solutions for a potential fundamental set. Okay, So we're asked to do a couple of things. It says determine if these form a fundamental set of solutions on the interval of all real numbers, and if so, we want to use them to give the general solution. So the theorem, one of the many theorems we just talked about, to determine whether something is a fundamental set of solutions, we need to show that it is linearly independent and that we have the right number of solutions in that set. We've already confirmed that we have the right number of solutions because for a 3x3 system, we should have 3 solutions in total. What we want to do now is evaluate the Wronskian of this set of solutions here. So Wronskian of x1, x2, x3. Okay, now what does that look like? Well, again, remember we're taking the column matrices here and just putting them in as columns of this determinant. So my first column is going to be 1, 6, negative 13. So 1, 6, negative 13. Now the second one, notice it's not just 1, negative 2, negative 1. We have the function e to the negative 4t being multiplied into this. So it's actually e to the negative 4t, negative 2 e to the negative 4t, and negative e to the negative 4t. Okay. Similarly, this column is not just 2, 3, negative 2. It's 2 e to the 3t, 3 e to the 3t, and negative 2 e to the 3t. All right. So being a system, being a 3x3 determinant, we can evaluate this using cofactor expansion along any row or any column. I think what I'm going to do is expand this along the column that contains only constants. So let's give that a shot. 1 times the determinant negative 2 e to the negative 4t, 3 e to the 3t, negative e to the negative 4t, negative 2 e to the 3t, minus 6 e to the negative 4t, 2 e to the 3t, negative e to the negative 4t, negative 2 e to the 3t. Okay, and then minus 13 e to the negative 4t, 2 e to the 3t, negative 2 e to the negative 4t, and 3 e to the 3t. Okay? Now, if this is going to be a fundamental set of solutions, we need this to work out to something that is non-zero. So let's evaluate each of these 2x2 determinants. Notice that every time I multiply by a diagonal here, I'm going to have a term with an e to the negative 4t in it being multiplied to a term with an e to the 3t in it, which is going to give me e to the negative t. And that's happening in all of these examples. So I know that every single term that is evaluated here is going to have an e to the negative t in it. I'm going to just factor that out from the very beginning and just deal with the coefficients now. So I'm going to have 1 times negative 2 times negative 2, which is 4, minus negative 3, which would be 7, minus 6 times 1 times negative 2 is negative 2, 2 times negative 1 is negative 2, so we have negative 2 minus negative 2, which is 0. And then I have minus 13 times 1 times 3 is 3, 2 times negative 2 is negative 4, and 3 minus negative 4 is positive 7. So we have 7 here. Okay? So I have 1 times 7 minus 13 times 7, which is equal to negative 12 times 7, or negative 84, e to the negative t. This is non-zero, and so that means we have a fundamental set of solutions. Now, if I wanted to form the general solution to this, I was off there, I would simply denote that by the set of all linear combinations of these, C1, 1, 6, negative 13, plus C2, 1, negative 2, negative 1, e to the negative 4t, plus C3, 2, 3, negative 2, e to the 3t. Okay? So I'm going to call it my set of solutions. And I'm going to say that this implies that we have a fundamental set of solutions because that establishes linear independence there. Okay? Very cool. Let's go ahead and move on to non-homogeneous systems. We just have a little bit left to cover here. So the way that we handle non-homogeneous systems of equations is very much the same as how we handle non-homogeneous equations back in 4.1 again. The idea, once again, is that we take a non-homogeneous system and we first look at the associated homogeneous system. What happens if we set that f of t equal to 0? We know that the general solution to that associated homogeneous equation, system of equations, will have a general solution that looks like this: the set of all linear combinations of some fundamental set of solutions, kind of like what we just found. In addition to that, if we can find some specific solution to the non-homogeneous system, the original non-homogeneous system that we were looking at, we will call that the particular solution, and the general solution to our non-homogeneous system, just like in section 4.1, is equal to this complementary solution plus that particular solution that we were able to find. Okay? And so here's an example to sort of wrap things up here. We're given this system. X prime equals all of this. And notice it's non-homogeneous because we have this coefficient matrix A times X plus some functions of t appearing in these matrices here. Okay, so we have here a non-homogeneous system, and we're told to verify that this rather complicated looking thing here is the general solution to it. And what we're going to do, rather than try and deal with this entire thing all at once, we're going to relate this back to this theorem we just talked about. So notice here the C1 and the C2 say that we're looking at all linear combinations of these two vectors right here. That would mean that this thing forms that complementary solution that we're talking about. And that would mean that this guy can be thought of as x1, and this guy can be thought of as x2. In addition to that, this right here doesn't involve any of those parameters, any of those c's, and so this is taking the role of that particular solution, xp. So what we want to do here is verify that these things actually do play the roles that they appear to be playing. And in order to do that, I would have to start by looking at the associated homogeneous equation and checking that x1 and x2 form a fundamental set of solutions to that. So let's do that first. What's my excuse me? What's my x prime going to look like if this is what my xc looks like? So let me say that a little bit differently. Xc is let's not deal with xc by itself. Let's deal with x1 and x2 separately. So x1 is equal to 1 negative 1 minus root 2 e to the root 2 t. Okay? What would x1 prime be then? Well, x1 prime, remember, I had said previously that even though we can multiply this exponential function in and differentiate each of these functions separately, we can also think of this matrix as a constant that's being multiplied to this function and just treat that as we would, differentiating a constant times a function. So this would actually just look like 1 negative 1 minus root 2 over root 2 e to the root 2 t. Okay? Now, if I wanted to go a step further, I could multiply this root 2 in. So this would look like, my t does not look like it's in the exponent. Let's change that. This would look like root 2 minus root 2 minus 1, bringing the root 2 in there, e to the root 2t. Okay? So now what I want to do is compare this to what would happen if I plugged x1 into just this part of my system. Because remember, if we get rid of all of this stuff, what remains here is the associated homogeneous system. And I'm trying to see that x1 is a solution to that specifically. So let's plug x1 into this. Okay, so if I did -1, -1, -1, 1, times x1, which is this guy right here, 1, -1, -√2, e to the √2t. Now I could multiply this scalar into this and then do the multiplication, but from our properties of matrices, I can actually do the matrix multiplication first and then just leave this scalar on the outside, which saves me a little bit of time. So if I did that, I'm going to get -1. -1 times this will turn these positive, so it becomes +1 plus √2. And then here I'm going to get -1. -1 minus √2. Okay, and so I have this e to the √2t. Let's simplify the stuff in that matrix there. -1 plus 1 is 0, and so I get a √2 up here. -1 minus 1 is equal to, it doesn't work out exactly. Let me see. E to the √2t. So I think we got something going wrong there. Let me just check my work here real quick. Make sure I didn't do... oh, yeah, I see what went wrong. So when I multiplied this √2 to this √2, I wrote it as a 1. It's actually a 2, isn't it? Yeah, that was just a mistake on my part. So this matches this. Those are equal, okay? Which establishes that x1 actually is a solution to that associated homogeneous system. We would do the same thing with x2. For the sake of time, and because x2 is so similar looking to x1, I'm not going to check that, but I'm just going to say verify that x2 is also a solution. Okay? ... The next step would be to show that x1 and x2 form a linearly independent set. I'm actually, we're going to pick this up in the next video. I can see that my phone is about to die, so I'm going to go ahead and stop this here, and we'll just finish this example in the last video.